Let's quickly review what we had. So application phase, we have some kind of differential equation, right? And then you have three different cases, right? Depending on what this thing is called the characteristic equations, e to the RT, whatever the roots of the R. If it's positive under the discriminant, then you get two distinct exponential functions, usually decaying. And then second case is if you have a double root, then you have this form, one exponential, the other one t times that exponential type of thing. And third case, the most common case but interesting case, is in case you get imaginary roots, then you have two different ones with the imaginary thingies in here, and you can use Euler's formula to convert it into cosine and sine. And amazingly, what happens here is, as long as you start with the real coefficients from the differential equation, these things, if this m, c, and k happen to be real, then a and b are real. Okay? So that's what we had before. Now, electric circuits. Okay, amazingly, differential equation looks exactly the same. So mathematics doesn't care. We just have to make enough physical interpretation. And you haven't learned this yet because you're not taking E&M or doing a self-study. But according to physicists, the voltage in a circuit, so we have a circuit. I think you might remember forgetting me mentioning something about LR circuit, this part, last year in the example. Okay, so we put a coil in something called the inductor with the inductance, and we put a resistor, and we did not put this capacitor in. Okay, then what I mentioned, and you have to take it for granted, the voltage in this across the resistor is known as R constant, which is a resistance times I. I is our variable. Okay, I is our function, amount of current in the circuit. Also, that voltage is same as this inductance times the derivative of I. That's how much I taught you last year. Well, used it as an example. Now, as you take E&M, also that's the voltage across the inductor right here. Now, the voltage across the capacitor is the total amount of charge in the capacitor divided by something called the capacitance, the constant that comes with the capacitor. Okay, now, and this voltage, external voltage across the source may not be constant. We can have some kind of function. Okay, so putting all of them together gives you this kind of differential equation then. U, so we have I, the derivative I, we have I, and we have Q, which is another different function. So you're going, how are we going to put this thing together? But here's the key. That current happens to be the rate of the charge changing in the capacitor. And that kind of makes sense because a capacitor is basically a rechargeable battery. If you charge it, the amount of the charge it loses is the current that goes around in the circuit now, isn't it? So this happens to be the case, meaning then we can convert all of them in terms of Q. See, this I is the derivative of Q. And then this derivative of I happens to be the second derivative of Q. You know what I'm saying? And then now we have a second order differential equation, exactly the same way we had it before. We just happen to have this arbitrary function. So this is non-homogeneous case. Good. So let's take this example. Say inductance, resistance is 40 ohms, and inductance is known as Henry, 1 Henry, to make algebra easy. And then capacitance is called, 16 times 10 to the negative 4th farad. This unit is called the farad. Okay, now, and then we have some kind of alternating current on the other side. Okay, 100 volt times cosine of 10t. Okay, then what is the current or charge in the circuit, in the capacitor? Okay, substituting everything, here's a 1. See this thing, this becomes 1, this becomes 40. Now 1 over, so the reciprocal of this becomes 625. And this is awful at the moment now, isn't it? But differential equations, mathematics don't care. It looks exactly the same thing. So we'll solve it our usual way. Okay, here we go. So we say Q, which is a function of, well, common. We'll just guess with e to the RT, the usual way. And then this thing becomes, of course, r squared e to the RT plus 40r and e to the RT and plus 625 e to the RT. And then we have to solve this homogeneous equation before we can apply it to the particular solution. Exactly same thing we did. So that becomes e to the RT, and then r squared plus 40r plus 625 is equal to 0. And as you can see, this thing, discriminant will be negative. This b squared minus 4ac. 625 is a big number, right? Okay, quadratic formula. So our r is equal to negative 40 plus or minus square root of 40 squared minus 4 times 625 over 2. Good. So that's negative 40 plus or minus u 400 minus, let's use a little trick because this is awful, right? Let's not do it like that. Let's see. Do you see a common factor 4 here and common factor 4 here? So let's factor that out. So outside is 2, and then square root of 400 minus 625 over 2. Okay, and of course this part, right? That's 15 squared, isn't it? 225. So we have negative 20 plus or minus, this thing cancels, so 59 is the solution. Okay, so our Q common happens to be e to the negative 20. Let's say common factor like this. I think you'll still get it, right? If I say C1 and then e to the 15, I'm going to write I first. Okay? I 15 t plus C2 e to the I negative negative I 15t. You still get it, right? Using this, but then I factor this out using rule of exponents. All good? Okay, then this is the part that I want to turn into cosine and sine. So this thing becomes e to the negative 20t, and then a cosine 15t plus b sine 15t. So far so good? Now what that tells you here is this is a sine and cosine, it fluctuates, but this thing is exponential decaying function, and this is 20t. So it dies really, really fast. Okay? Once you turn the circuit on, this is known as the initial spike. Okay, I'm not sure, you guys only have seen, do you remember this big weird TV? I have one in the classroom before the flat screen. You remember this big cat that, I mean, in the elementary school, the teachers had it on the top corner. When you turn that thing on, that screen was like little weird, and then it stabilizes, right? That's this part right here. there is a huge spike, and then this a and b is usually pretty big constant, but then this exponential function kills it off, so it disappears pretty fast. Okay, I'm going to come back to this a little bit later, but now using the particular solution. So now we are solving this. Let me rewrite the differential equation. It was second derivative. I'm going to write it as MIT's notation. Second derivative q double dot plus 40 q single derivative. MIT uses this dot as a time derivative plus this convenience 625 q is equal to 100 now cosine 10t. 8. Okay. Now, so we try this. Q is equal to e to the RT again, right? Can we, oh, Q, not, I misspoke, not e to the RT, but whenever we have sine, cosine, or cosine, we have to use something that could give us sine and cosine, right? So only thing that we'll do is, we already used A and B here as a constant, so C, and then cosine 10t plus d sine 10t. We use this as ansatz. And then if you take a derivative and twice and then mix it up, then we'll get something like this. 8. Okay, so let's take a derivative of this. Q dot is equal to negative 10c sine 10t plus 10d cosine 10t. 8. And then Q double dot, this is a particular solution. Double dot, second derivative is negative 100 c cosine 10t. This thing turns into minus d sine 10t. Y'all with me? Okay, now we have to shove all of this into this. Okay, so this plus 40 of this plus 625 of this. This is horrible. Okay, let's do it. So we have negative 100 c cosine 10t minus 100 d sine 10t, like that. Okay, minus, and then I have to multiply 40 to this. Good. So we have 400 c sine 10t plus 400 d cosine 10t. So far with me? And then I have to multiply this by 625, this thing. So plus 625 c cosine 10t plus 625 d sine 10t here. So far so good. And that's the other side, 100 and cosine 10t. Okay, collecting sines and cosine. Now let's see what's cosine term. We have cosine term here, and cosine term here, and cosine term here. Okay, so we can add these two. So we'll have 525c, and then here's the cosine term, which is 400 d, and then cosine 10t, 8, plus, let's do the sine term now. Here's a sine, here's a sine, here's a sine, but these two are d's, so we can combine these two. So 525d, and then negative 400. So we have negative 400c plus 525d sine 10t. 8. And that is equal to the other side, 100 cosine 10t. You with me? That tells you we have a system of equation 525c plus 400b needs to be 100. And the other one is negative 400c plus 525d is equal to 0. Eh? Oh my god. Divide both sides by, what should we, 20? 20 divide this both sides by 25. So this thing tells you 21c plus 16d. I'm totally doing this in my head. And this thing becomes negative 16c plus 21d is equal to 0. And since this is too much algebra, if I do this in my head, which will give us 84 over 697. This is where the matrix calculator, matrix thingy in your TI-84 comes in mighty handy. Do you still remember how to do matrices to write to? Yeah. 697. Also, answer key helps a lot. Okay, after ugly algebra, this is what you get. Okay, so particular, we have this thingy, right? Okay, after common factor 4, so Q particular is 400 or 4 over 697, and then we'll have 21 cosine 20 plus 16 sine 20. Okay. Now, then we can put it together now. So we have Q. Remember, Q is equal to this thingy plus this thingy, right? So from earlier, we had e to the negative 20t. And then we have a cosine 15t plus b sine 15t. Now we have 4 over, why am I writing this? Undo. Okay. I'm gonna copy and paste. It does not want to copy and good. You know, OneNote can be so hateable sometimes. Paste. It doesn't want to paste. Really? Copy. Paste. Oh. In that time, I could have just written this whole thing by hand, right? Anyway, that's the whole thing together. Now, shall we apply initial conditions and solve this? Yeah. So initial condition, oh boy. So if we choose at Q0, let's say original charge was 0 in the capacitor. We just switch the circuit on with nothing in it. Okay? That tells you we have 0 here, so this thing becomes 0, so we have just A. So 0 on the left-hand side is A plus this thing is still there. You know what I'm saying? So that is 84 over 697 U from way up there, that thing. So that tells you A is negative 84 over 697. And then let's say initial current was also 0. So there was nothing in the circuit before we throw the switch on. Only thing that's doing anything is that 100, the cosine term, this thing. This thing is the only thing that's, so the battery was empty and there was nothing. Okay, which is typically the case in the electric circuit. Now, the whole horrible thing is we have to take a derivative of this. and plug in 0. Oh, so that 15 will multiply to this B, good? And then this thingy, derivative, yikes. Let's suppose we did that. So you will get this 1680 over 627 plus 15B plus 640. I'm totally doing this in my head. Okay, and B will turn out to be negative 464 over, oh my god, right? I'll just copy and paste the final answer to the notes because this is too horrible. Okay, let me make it appear down here with my other computer. Okay. What is it? And this is the answer you will get if you plug in everything correctly. Okay. And let's take a look at this current. Even this, right? That 63 and 116 is pretty big compared to 21 and 16. You know what I'm saying? And then the initial current, this is like the spike that you will see on that old TV. Current, initially, see, here's an exponential decaying function. This thing is almost 2000, right? Compared to, well, okay, this is still kind of big. And this part is what causes the spike. But that exponential decaying function kills this thing off pretty quickly, so only thing that remains is this part. This is known as the steady state. Steady of the circuit. So like first half a second, maybe, this thing. So circuit is unstable, so it's not going to do what you want it to do originally, but eventually this is the only thing remaining. And notice that frequency here is 10, where this is 15. So you have different frequencies, right? So here is the 15, which is the natural frequency of the circuit. If you didn't have any voltage on the outside, and if you have some kind of charge in the capacitor, then this will oscillate back and forth and eventually die off with this kind of thing. And this is what your power outlet gives as an alternating current, right? And this thing eventually wins. So whatever your energy that you're feeding into the circuit is what drives this circuit, but you have this natural thingy here, okay? Here's a little unfortunate case. So that it happens, if this natural frequency of the circuit happens to be exactly same as this. So if this were 10, because of this inductance and resistance and capacitance, it could be the same. I mean, chances are pretty small, but in case it turns out to be the same, then we couldn't have used this just cosine and sine here, right? Because what are you supposed to do if this is 15? If this were 10, then we couldn't use just 10. 10 is the same thing. So we have to multiply t in front here and here. What happens is then this thing will still die, but this part, you have a t in front. So this will grow forever. The spike will get bigger and bigger, and it adds on to this, and the whole circuit blows up. There is a possibility. And similar thing happens, anything that is vibrating has a natural frequency. Have you heard about this, the platoons, so soldiers walking on the bridge and the bridge collapsing? Because when the soldiers march, they march with the lock steps. Everybody steps down at the same time. And then bridge is supposed to vibrate with the wind or whatever, just like a rubber string, violin, guitar string. If if you're unfortunate enough to have that natural frequency of the string to be exact frequency of the bridge happens to be exact same natural frequency of these soldiers stepping, then that it's kind of imagine if you're jumping up and down on a trampoline. How do you make it go higher and higher? Because you're controlling with your leg, and then the exact same frequency of the trampoline, you can amplify this forever. And that's how you can achieve that kind of jump. So same idea, that bridge becomes a trampoline, and then eventually bridge will give. So there is a command in the military, which means that you just walk without that being in lockstep. Because soldiers are always like so comfortable doing that, but like, no, don't do that on a bridge, because you can, that bridge has collapsed before in history. Tesla has this attempt to, because each building has a little bit of frequency that, especially the tall buildings, vibrate with the wind, and that has a natural frequency. So Tesla decided to invent a little thingy. Maybe he can bring a building down with that. Whatever you hit this beam is exactly the same frequency. I don't think there's no writing or record of any kind that Tesla actually pulled it off, but in theory, that is possible. Supersonic jet fighters. That's why there's a maximum speed of that jet fighter, because the wing itself will vibrate because of the wind. Because you cannot make it perfectly rigid, that'll just break. It's too brittle. So it's somewhat flexible, so the jet fighter wing will vibrate with a natural frequency. And you have to make it thinner and thinner before you can achieve more speed. We still have enough powerful engines to achieve almost any speed, because if you have a rocket, space shuttle, I mean, these things can really go. So that we can put bigger engines on the jet fighter, but as these planes accelerate, the wing will vibrate more faster and faster and faster, and then eventually that frequency will be exactly same as the natural frequency of that wing. I mean, it's pretty high, but it will eventually get there as you speed up, and that entire wing will just either tear off or not do what it's supposed to do because it's vibrating too much, and then that's when the jet crashes. So that's the maximum speed of that fighter jet. You get it? Okay, so for that reason, space shuttles and rockets have a very tiny wing, because you're not really depending on that wing to go up into the orbit. You're just solely relying on the engine itself to achieve that orbit. Okay.